Hi everyone, this is the Unit 13 exam review for Geometry A, and this was our chapter on circles. So looking at number 1, in a circle with radius 210, I'm going to try to draw this to the best of my ability. So here's our circle. Our radius is 210, which means that I'm going to draw 2 of these. I know I'm going to need those in a minute. And each one is 210. And I want to find the length of a chord of a 150-degree arc. Remember that a chord is this segment that runs like this. So this is what I'm trying to find. And when it tells me that it's a 150-degree arc, that's technically this, but remember that that 150 matches with the central angle. So we would also know that this is 150 as well. Okay? So looking at this, what I really have is a triangle with two sides that are each 150. Nope, just kidding. Two sides that are each 210. An angle in the middle that's 150. And I'm trying to find this, which is x. Remember, we learned this right off of our trigonometry unit, which was really nice because what we're going to have to use here is the law of cosines. So from here, I would set this up by doing, here's my formula for law of cosines. And in my class, we always talked about whatever we were trying to find, whatever our variable was, we called that A. So here where I called this side X, I'm really going to think of that as side A, which would make my 150 angle A. And then sides B and C are just these two. Doesn't matter which is which. And in this one, it really doesn't matter because they're both 210. So when I set this up, I would say A squared equals 210 squared plus 210 squared minus 2 times 210 times 210 times cosine of 150. The nice thing about this one is that all of this can go straight into your calculator. So give me just a second to type that in myself. And I end up with A squared equals 164,583.44. And then remember, that's actually equal to A squared, and I want A. So from here, I need to make sure I go in and take a square root of that. Okay, and so for my final answer, I get that side length is 405.7. And always make sure that kind of makes sense with the numbers that you're working with. If my other two side lengths are 210, 405 is a reasonable number. If you got like 12, for example, that would not be reasonable. If you got like 7,000. Some of you might think to stop at this 164,000, but hopefully you would realize that that number does not really make sense with the 210. Okay, the next two are almost exactly the same, so I'm going to see if we can set them up and just start right here at this point, okay, without having to draw the picture, because I think that you can do it. If you need me to go back and draw a picture, feel free to ask in class and we can go over that, but I think that you can handle this. So for this one, if the radius is 55, that's like our side length, that's B and C, and here's our angle A. So I would do A squared equals 55 squared plus 55 squared minus 2 times 55 times 55 times cosine of 60. Type that all in. So for that first piece, I get 3,025 exactly. And then remember to take a square root of that. And I get 55. Oh, and I guess I should have realized that, if you think about it, that this would have to be an equilateral triangle if it's a 60-degree arc. Yeah, so this is actually, if the radius is 55 and 55, that third side is also going to be 55 if you're working with a 60-degree angle. Because again, you would know then, if these are both 55 and these are 60, if these two angles had to be equal, they would each have to equal 60, and that would give you an equilateral triangle. So if you caught that ahead of time, that could have maybe saved you some work, but otherwise, that's just an interesting observation there. Okay, number 3 is almost the same thing. The radius is still 55, but now we've got a 144-degree arc. So I'm going to use this same setup, except this 60 is going to change to a 144. Let's take a look at what that would look like. So a squared equals 55, 55 squared plus 55 squared minus 2 times 55 times 55 times cosine of 144. Now this one's not going to come out to be equilateral because we're not working with a 60-degree angle. I end up with a squared equals 10,944 0.55. Take a square root, and I get 104.6. And that's correct for your final answer. Okay, number 4. Find the measure of arc CB. Well, arc CB is here. And the intercept, or the angle that intercepts that angle, or that arc, gosh, I can't speak today, is this one here. So the 53-degree angle intercepts this arc, but what kind of angle is that? That's an inscribed angle because the vertex is over here. Okay, if the vertex is on the circle itself, it's an inscribed angle. If the vertex is in the center of the circle, you're working with a central angle. So this is inscribed. You may want to make a note of that. And remember that when you're working with an inscribed angle, the angle is half of the arc measurement. So all we have to do is take that 53, 53, and double it. 53 times 2 is 106. So this would be a 106-degree arc. Okay? And again, you can think of it either way. You can say that the angle is half of the arc, or you can say that the arc is double the angle. Okay, let's take a look at number 5. Arc ABC. Well, arc ABC goes all the way from here to here, from A to B to C. And I really wish they would tell us if this is a diameter. You know, I think we have to be careful here. I don't think we can assume it's a diameter, but many of us will. Because this doesn't show necessarily the center of the circle, we don't know that this is a diameter. So here's the approach I'm going to take with this one. I'm going to start by looking at this arc up here, ADC. And that is intercepted by this 89-degree angle, which means, again, that 89 degrees is an inscribed angle. So that would mean that this measurement up here is double 89, which is 178. And I know that the whole circle is 360, so to find arc ABC, I would take 360 and subtract the piece I don't want, which is the 178. It comes out to be 182. So again, be careful with that one, because if you assume that that's the diameter of the circle, you would get 180. But because it gives us this 89, we can't necessarily assume that. So just be careful with that. Okay, let's take a look at number 6. Okay. It says AB is the diameter. AB is perpendicular to CD. So we know this here is a right angle. And line L is tangent to circle O at point A. So this is a point of tangency right here. Can we justify that DE is equal to EC? Well, this one to justify is, they give you a little more information than you need to justify this question. Because you know that AB is a diameter, it goes right through the center, okay? And CD is a chord, and this is a right angle. We have a theorem that we learned way back when we first started talking about circles called the chord center theorem. And one of the things that theorem said, there were a lot of pieces to that theorem, but one of the things that that theorem said is anytime you have a diameter that's perpendicular to a chord, it bisects the chord. Okay, so that would mean that DE was equal to EC because it's being bisected. So really, the idea that this is a tangent line you don't necessarily need in this situation. I guess we could ask you to do some further justifications later on, but with this particular question, that's all you really would need. Okay, happy studying.